Hello everyone. Today let's solve a hard geometry problem from SuMON Fortnight worksheet of level 4. This problem states that you have a triangle, you have extremely small point-sized mirrors on the vertices of the triangle that faces the external angle bisector constructed at each vertex of the triangle. So now you are allowed to consider a point inside the triangle, and you are going to prove that there exists a point again inside the triangle which is the location of the real image formed by reflection upon these three mirrors. So let's take a closer look into the solution of the problem. So here is the question that gives you the actual statement. Let us consider the image of the question. You have a triangle, and as given, you have the mirrors placed facing the external angle bisector. So they are placed in this way and in this way. Now take a point inside the triangle, and that is also the position of the object. You have to prove that the image of the object also lies inside the triangle somewhere, and also the image is going to be real. This image is clearly formed by the reflection about these three mirrors. But we will take into consideration the location of that, before which we will be studying the trigonometric form of Seva's theorem. This is going to be extremely useful in our proof. Consider a triangle ABC and construct CVNs. CVNs are the line segments connecting vertex to a point in the opposite side. So if you join it, you get a CVN, and you get a CVN, and you get a CVN. Supposing these three CVNs constructed from the three vertices concur at a point, then it summons a theorem called as Seva's theorem, which governs the location of these 3 points, say D, E and F. But we are going into the trigonometric form of Seva's theorem, which is derived from the Seva's theorem called as trigonometric form of Seva's theorem. Let's see what it is. Let's call this angle to be alpha 1, alpha 2, this one to be beta 1, beta 2, and this one to be gamma 1, gamma 2. Now, it states that sine of alpha 1 by sine alpha 2 times sine beta 1 by sine beta 2 times sine gamma 1 by sine gamma 2 equals 1. So this is the condition that determines the concurrency of these three CVNs, AD, BE and CF. AD, BE, CF concur at a point if and only if these three ratios multiply to 1. Alright, now let's take a look into some basic principle of reflection. Suppose you have a reflecting surface and you have the incident ray falling on the reflecting surface, and you have the reflected ray. Call by I the incident ray, call by R the reflected ray. Now suppose you construct the normal at the point of incidence. Which is 90 degree or perpendicular to the reflecting surface. Then the fundamental law of reflection says that incident ray I and R make equal angle with the normal at the point of incidence. Now this equivalently says that the angle made by the incident ray I and the reflected ray R are equal with the reflecting surface. So this is again one more aspect we are going to use for our proof. But the first and foremost one will be the trigonometric form of Seva's theorem. Alright. As per our given configuration, we get this diagram for the triangle and the angle bisectors. So shown here by this CVM is the angle bisector, and it is external angle bisector. So you will have the mirror placed like this, that is at 90 degree with the external angle bisector, so that it faces the line AD. Similar goes for all the others. But it is quite crucial to notice that this angle entirely is 180 minus A, and the external angle bisector divides the external angle into two equal halves, giving us 90 minus A by 2 and 90 minus A by 2. Alright, let's erase the other one. Let's consider angle CAD, which is 90 minus A by 2. Similarly, consider the internal angle bisector. Now, what do you think the angle made by the internal angle bisector with CA is? It's A by 2. And the sum of these two is 90 degrees. So they are complementary angles. So something interesting is happening. What is it? That the mirror is placed along the internal angle bisector at the vertices, because it is 90 degree to the external angle bisector. Now we will incorporate this with the second principle we studied. So along the internal angle bisector, you have the mirrors placed, and we are considering a random point inside the triangle, say P. And we are going to locate the image formed by reflection about these mirrors, these three mirrors. First, notice that when the incident ray from P is incident on the mirror at A, then it will get reflected where both incident and reflected rays form equal angles with the internal angle bisector. And therefore, this can be depicted in the following way. If you consider the point P and join it with AP, the reflected ray is nothing but the ray that make equal angle with the internal angle bisector at A. So it's like this. Now similarly, BP is the incident ray. BP is the incident ray. Let's draw the reflected ray with blue, and it will be the ray that makes equal angle with the internal angle bisector at B. And now these two will intersect, and that is the point at which the image is obtained after reflection. Alright, the question then would be, what about the incident ray PC? Will it also pass through the same point as the other two reflected rays? Because if that is not passing through, then the image can be in multiple places, in multiple locations. We want an image to be concentrated at a particular point to get a clear image. So all the reflected rays are expected to pass through this point. All three incident rays are getting reflected about the mirrors at these vertices and are expected to pass through this point. Okay, so to answer this question, first we notice that the angle made by the ray AP, that is the first incident ray, let's say it is theta and alpha. You can take for example, just for example, this is not for the rigorous proof. Say the incident ray makes 10 degrees with CA and 50 degrees with, or 60 degrees with AB. Then the reflected ray is the reflection about the internal angle bisector. That is because you have these two angles equal, because incident and reflected ray make equal angle with the mirror, and therefore they are reflections about the internal angle bisector itself, and hence this angle is sort of taken and put back here, and therefore this angle will be now 10 degrees, and this angle made by blue with the line AC will be 60 degrees. They will get swapped. The reason is because this angle, the one here, will be equal to this, because they are reflections of each other about the angle bisector. So if these two angles are equal, then those two angles are also equal. Now I know this plus the angle made with internal angle bisector twice is 60, and therefore this plus this will be 60 as well, and therefore the angle gets swapped upon reflection. So now all the three reflected rays are just swaps of the incident rays about the two sides adjacent to that angle, and therefore we can now consider the angle made by the lines AP, BP, CP with their sides. So in order to be pertinent with the trigonometric form of Seva's theorem, let's be consistent with our notation. We will use the same notation as before. So since these three CVNs concur at P, of course if you extend them they are just CVNs, so we have truncated them, you get the same expression sin alpha 1 by sin alpha 2 times sin beta 1 by sin beta 2 times sin gamma 1 by sin gamma 2 equals 1. Now, if you just take reciprocal to each of these ratios, then you will obtain sin alpha 2 by sin alpha 1 times sin beta 2 by sin beta 1 times sin gamma 2 by sin gamma 1 equals 1. And this implies that the reflected rays that form alpha 2 with the side AB and alpha 1 with the side AC and so on, the beta 1 and beta 2 gets swapped with the reflected ray, and the other angle will also be swapped. That is, this will be gamma 1 and this will be gamma 2, will also concur at a point because of this inverted trigonometric ratio of Seva's theorem implies that reflected rays concur at a point. The reason is because the reflected rays just form angles that are swaps of the angle made by the incident rays. Therefore, they will also concur at a point inside the triangle, and this is the location, say Q, of the image formed by reflection. So we incorporated several ideas from several parts of mathematics itself to solve this problem. And this is how we make the problem more interesting and intriguing. We try to incorporate real life questions to the problem so that the kids get intrigued, and even some kids make experiments out of these kind of problems. So we will meet with more interesting problem in the next problem solving video. Stay tuned then. Thank you. Bye.